Delta Cepheus, a world-changing star. So anyway, I mentioned that I had started astronomy seriously into astronomy in about 1986, and one of the things that was going on at that time were a number of star parties. Star parties are campouts for astronomers, and usually under fairly good skies. But the star party that I pretty much started out with was one that was held in Kankakee. And in fact, the Kankakee aspect of this, the Astrofest angle of this, really has to do with my first contact with Delta Cepheus. Delta Cepheus, as a variable, held out very little attraction for me at the time because I didn't know much about him, but I was kind of interested. And Astrofest was the way that I found my way to it. If you know anything about Astrofest, anybody here that had been to Astrofest? Just no one's heard of it. Wow, that's unbelievable. That's because you're in Northeast Indiana, I guess. Astrofest was started by the Chicago Astronomical Society. It started in 1979, and through a lot of internal problems that they had at Chicago Astronomical regarding Astrofest, it ended up withering away in 2003. But that's actually quite a good run. And at its peak, Astrofest hosted over 1,200 people in a, I don't know, 4 or 5 acre kind of a area that was used by the Boy Scouts. It had been a hog farm at one point, and so if you had the unfortunate luck of being out there shortly after a rain, or if it rained when you were there, you were actually reminded of that fact. And one time it was even a problem because the groundwater became contaminated, and so when you went into the bathrooms, you ran into signs that said, "Don't use the water, not even for brushing your teeth." And so there was a lot of bottled water available. So it was a very, very interesting place. Now, 1,200 people is a lot, and about, I don't know, 98 to 99% of them were men. And you can imagine then how the facilities were after 12 hours, 24 hours. It really got to be a challenge not to get ill. But that was the good parts. Now, it actually was known for 3 things. Camping was one of them. Telescopes, DYI telescopes was another thing. Vendors was another thing. And you say, well, if you go to a star party to look at the sky, right? And the answer is, well, not necessarily at Kankakee, because although it was outside Chicago, about 20 some miles to the south, maybe it was 30, but it was close enough. The Chicago Light Dome pretty much dominated. And so you didn't really go there for pristine skies. You went there for the camaraderie. You went there for the telescopes. At that time they were doing awards for film photography, things like that, and to look at the vendors. So what you see here is just a hint of what the camping was like. At its peak, they had it laid out in a grid. You had to put your tent within this grid that you didn't have to pre-buy it. You just had to find an open grid and get inside of it. They'd leave lanes for vehicles to get by. And that was a good thing, because one night some guy wandered out of his tent and found the only cliff that was in the area and fell over it and into a tree. And at about 3 o'clock in the morning, we had an ambulance zooming by our tent, and not more than 5 feet away from sleeping astronomers. So that was kind of an experience. But that was the kind of thing you did. You know, you had a lot of experiences. Saturday night, of course, was dinner night. They had a feast that they put on, and you got in line with all kinds of people and just chit-chatted. It really was a very good place to be, but not necessarily for the skies. Having said that, I had the best view, I think, ever of the Swan Nebula there, the Omega Nebula, and a few others. So it actually was okay. Okay, telescopes. I did mention DYI telescopes, and you really got to see an unbelievable number of telescopes there. This telescope is some sort of an English kind of a mount. I'm not even sure how big it was. You can see that it's an enormous F number, probably a 6-inch F15 or something. Just nothing but a planetary scope. Very interesting. This white one had always been one of my favorites. Just a beautiful hardwood kind of fork mount design and on a trailer. It really was something to look forward to in this Astrofest venue. Down here, we just have a kind of a panorama of culture scopes, a couple of DYI scopes, and the nascent portaball right here. I don't know if anybody had ever heard of portaball. Portaball, yes, no. Okay, so anyway, portaball, you can see it looks like a ball. The yard scope was always there. I think that was homemade. And from the Cincinnati Club, there was a man named Ron Raffenberg, who Ed may or may not know. He was in the club for a long time, designed a scope that was really portable. And as you can see, it just had two arms on it to hold up the secondary. And it all collapsed into the rocker box at the bottom, and it was very, very portable. A number of people copied that, a little bit bigger sizes, like a 6-inch. This was about an 8-inch, and he had a variety like that. They had a telescope making contest that you could enter, and this poor guy entered his telescope after it was upgraded, and I never heard from them. I didn't win. Yeah, exactly. Someone I don't know anymore. Vendors, it was really an interesting place for vendors. The thing that was interesting about it, you had Roland Christian from Astrophysics come out with all of his new wares. He would sell telescopes there. He would deliver telescopes there. You could see what was coming out of his shop, and his prices and his delivery times at this time were much, much better than today. If you buy an Astrophysics today, you may or may not live to see it delivered. The 5 and 10-year delivery times are not unusual. But they were very recent, or very, very good at that time. My brother-in-law bought a 6-inch F9, and it took only about 4 or 5 months for it to be delivered. And his thought on that today is, I wish I would have bought 2. They're so expensive. Kriege from Obsession was always there. He would take orders. He would deliver telescopes there. This telescope right here is the first meter grade telescope, 36-inch telescope that he had built and delivered. And we got a chance to look at that. I later ran into the owner of this telescope down in Texas, and under extremely good skies down by the Fort Davis Observatory down there at the University of Texas telescope. We were in the parking lot of what was called the Ultimate Star Party, and there were like 3 36-inch telescopes there. It was really a lot of fun. And I mentioned portaball. You see that here. And then this was a really interesting, really interesting telescope. I wish I would have purchased this one. This was a Lightspeed. It broke down into 3 pieces. Really, really nice design. Just didn't pull the trigger. If you're interested in making telescopes, you could find ATM parts. A lot of people sold telescopes that were there. You could find astro art. You could find just about anything that was sort of related to astronomy in the vendor field. I unfortunately I don't have any pictures of the vendor field for some reason, but it was really packed and always a pleasure to go through. So astro art and books. Well, books is one of the links that got me connected with Delta Cepheus. And in fact, in about '96, I was looking through the antiquarian books that were there and some newer books, and ran across a book by David Levy. And I still have that book. Let's see if we can get that up. There we go. Observing Variable Stars, A Guide for Beginners by David Levy. So in addition to his book, you could find things by the author Moore. He always wrote nice, complete guides to viewing this or that planet or this or that kind of object. They were always good to have on hand. This one's from '68, I think, kind of dated. And on the antiquarian side, I ran into something called Galaxies, and it was authored by one of the people that will be featured a little bit later. And I don't know. I'm not seeing his name. Harlow Shapley. I should have known. Harlow Shapley. So books were also another really interesting part of part of what you could get there. Also eyepieces, maps, whatever you needed for your astronomy needs. So in the Observing Variable Stars book, the opening section in that, or at least the section introducing how to actually do photometry, was a couple of pages on Delta Cepheus. Delta Cepheus is a well-placed bright star that has a kind of a compact period of about 5.4 days. And it explains how you go about doing visual observations of variable stars. You get your reference stars. Is it brighter than this one, dimmer than this one? And eventually you can train your eye in order to figure all this out. And so I picked up the book and I read the section, not much more of the book than that section. I mean, you know, I had other interests other than variable stars at that point. And went back to my house in Illinois and just kind of walked out the front door on a few evenings, looked up, and actually saw the star vary. I mean, it was varying a whole magnitude. So by using his methodology of just comparing it to the stars around it, you could actually tell and you could see when it was getting dimmer. I had to happen to have a few good nights in a row, and you could see it dimming. Now, you could see it dimming within your lifetime. I mean, you know, 5 days is not exactly long. It's almost like a Fast and Furious experience watching a star, which is supposed to be fixed, unchangeable, unchanging, just kind of drifting by in the night sky. Well, this star was changing. It's like the Galilean moons of Jupiter. It's like Mars rotating. It's like the Great Red Spot going across the planet. A star, not a planet, but a star going through its activities. So that impressed me. Even to this day, although I'm not a big variable star enthusiast, I still remember that because it really was so surprising. So let's see if we can. So what exactly did I see? This is supposed to be an animation, and it's supposed to be animating. There we go. So this is approximately what I was seeing. Hopefully you can tell, you can see it. Now, in the sky, you won't actually see the crosshairs. I have to, full disclosure, that was added just in case you were wondering what it was that you're supposed to be seeing in this. But that's basically what I saw. And I tried this animation a number of different ways. And one of the ways was actually trying to make the star dimmer. You would think that would be the way to go. And it didn't look any different. No matter how dim I made it, it always looked the same as the stars around it. So I went with an area to be proportional to the magnitude. So it kind of gives you the idea of what it's supposed to be. But this is one of my astro photos with the animation superimposed on top of it. So that's what you'll see. I thought it was pretty cool then, and I like the animation, but make your own judgments. Anyway, so what did we really see? We saw a Cephid variable. Cephid variables have a quick rise to the maximum. It only takes about 1.4 days. A relatively slow fall to the minimum, 4 days. So there you get your 5.4. They only change about 1 magnitude, but it's visible. I can tell you it is visible, not really difficult. And the regularity of its activity, it's like good clockwork. It's simply the same all the time, millions of years. And that's what we're looking at here is a light curve for Delta Cepheus. And this light curve, if you look at the dates, we've got dates from back into the 90s, into the 2000s, 70s, 77 through 79, 1946 through 1961. So all of these different colors, as you can see, correspond to these different observers and their contributions. And it's a very handy tool, as it turns out, for a lot of other activities other than keeping track of what variable stars are doing. So light curve is typically calibrated either with the starting point at 0 or at maximum. And typically I've seen them at 0, so I'm not really quite sure why they chose to put it at maximum. But, you know, as long as you understand it, it's okay. The phases, usually along this axis, you also have them in Julian dates. Julian dating is important so that you can coordinate all of your observations, whether they're consecutive or whether they're one today, one next month, one next year. You can figure out what phase that they're in. This is talking to us about phases here. These all have Julian dates corresponding to them, and that's what allows you to take future observations and put them in the right order so that you can build this sort of a light curve. Very handy, because as all of us know, you have more cloudy days than clear days in Indiana. So you need a tool like this in order to make it all work. You also see it being completely regular. There is no randomness to it. It's all very tight. And that's what you'll get with a Cephid. And that's a really good thing. Okay. So that was my first contact with Delta Cepheus, was just reading the book, getting out the front door, and taking a look at it. And that occurred in the 90s. So fast forward an incredibly short, less than 30 years, and I get involved with the spectroscope, and there's a spectroscopic program in the Astronomical League's list of programs, which I, by the way, recommend. If you're looking for any way to organize your viewing, the League has got a bunch of projects that will help you do that. And one of the entry programs that you should work on is the Stellar Evolution program, and it takes you through all of the star types, with Delta Cepheus being one of them. There's a section on variables and a few others. And so my second contact with Delta Cepheus was the Stellar Evolutionary program, and my log entry for that is binary, maybe. And Cepheus, Delta Cepheus, is a bright yellow, and a second star, which I took to be its binary companion, was bright, half the brightness of Delta Cepheus, and reddish. Well, it turns out part of it was right. It is a binary. Cepheus can look yellow, but its companion star is actually like a B star, so it's blue. And my only defense here is, well, I can't say that I'm partly colorblind, because although that's true, I decided it was red and not blue or some other color, which would normally be the case. But I did look closer at my entry, and it turns out I was using a wide field eyepiece, and I think I mistook a red star, and we'll see that red star in a couple slides. So I'm going to stick with that story, that it wasn't just a random color drawn. There was actually a star in the field of the right color, and you'll see. The third contact was the League's spectroscopic observing program, and I took many sets of data for that. I have 6 sets, like it says here, and at the time, the configuration allowed me a resolution of about 3,000. So it took 3 slices, and this is a joint set of data. And I think one of the major features here is it's a bit noisy, and I can confess that it's not instrument corrected either. I don't have an IRC curve to smooth all this stuff out. You can tell that because of the kind of lumpy, high end, a red end of it right here. Since then, my spectra has gotten a lot cleaner, better technique, but after 2.5 years, you'd hope so, and it has become better. So personally, I've had 3 good contacts with it, and I still find it a fascinating star. And when you look at the characteristics of the star, it really does become even more interesting once you get beyond the fact that it's just changing a full magnitude. So where is this star? Well, it's in Cephus, right? So that's a good starter, since it's Delta Cepheus. And it turns out that it's off of one of the keystone stars. I hope this is Zeta. My Greek letters are not real strong. But it's a keystone star, and so it's not hard to find. It's also circumpolar, and it is fairly bright, so you really don't have much trouble finding it. So it is available year-round. Now, the AAVSO provides healthy support for all variable stars, it seems, and you can get finder charts. And in fact, this thing that we looked at over here on this page, this is one of their finder charts, and it gives you details about it has a zoomed in kind of a finder chart, as well as one that covers a wider area to help you find it. And these numbers in here indicate the brightness of these stars. So the 7.0 here is actually 7.0, and the 5.9 here that is not 59, it's 5.9. And so these are your reference stars so that you can make your observations of whichever variable star you're looking at. Okay, so let's see. So it's not hard to find, and it's bright. So again, get out and take a look. You'll be impressed at what you see. So what is Delta Cepheus? Well, I've said that it's a variable. I've said that it's easily found, and what it is an F to G type luminous giant star. It's very it's very large. So we know that's what its baseball card says. It's a F5 IB to a G2 IB. Are you familiar with the circle dot notation? Circle dot notation indicates that this is in reference to the sun. So you read this as 1 to 2.1 times the temperature of the sun. So T with the circle dot. So what that means is that we're looking at something that's about 5,800 to 6,900 degrees Kelvin. It changes quite a bit. Its luminosity is 2,700 times. This is more of a power output kind of thing for the star. 2,700 times that of the sun. It's about 5 solar masses. So it's big. Its radius is 44.5 times the sun. So this thing is big, and its absolute brightness is a minus 3.49 to 3.3 versus the sun's, which I should have that. Where is the sun? Oh, versus plus 4.8. So minus 4.3 versus plus 4.8. So we're looking about 8 magnitudes difference. So that's about 1,600 times brighter than the sun, just in visual magnitude. And the distance is about 900 light years versus 93 million miles from the Earth. So you've got this star that's changing 1,000 degrees Kelvin that is driven by a change in its diameter. This thing that's 44.5 times the radius of the sun is contracting and expanding on a regular basis, that looks like clockwork. That's pretty amazing. I mean, think about that for a minute. Something bigger than this, a lot bigger than the sun, is actually pulsating. It's actually changing size, changing temperature. That's pretty cool. You see, and you can see this happening out your back door or out at the observatory. So that's what we're dealing with, is this, a variable star with these kind of statistics.
Hey,
yes, sir.
What is the physics behind that?
We will get to that. We will get to that. We will wade into an area that I know nothing about. But I have some words that explain it. And hopefully, I was hoping Ben would be here, or Dan Gall would be here to pick up the thread for me. But they're not here, so we're going to have to just kind of let that go for a while. So let's see. Other characteristics of the Cepheid variables. The maximum brightness occurs when the star is most rapidly expanding. Minimum, you can read this here too. Minimum brightness when it's contracting. In the HR diagram, the Cepheid variables fall in this area. They're between main sequence and the red giant region, something called the stellar instability zone. And since the thing is changing size and temperature, seems like it's unstable. Its instability is due to the core fusing helium into carbon and oxygen. And the pulsations are driven by something called the kappa opacity mechanism. There. Got that? has something to do with the helium ionizing at a certain rate. Sometimes it's higher, so it absorbs more energy, and the star contracts because it's not as hot, and then it stops absorbing the ionization. The helium isn't as ionized. I know it's pathetic, but I don't understand the physics, and I don't think I could really learn the physics in that short period of time. So let it go with that. But there is a mechanism for it, and another interesting little factoid I picked up that said that these Cepheids are going to pulsate until they simply run out of helium to fuse. And then I guess it'll go and turn into a white dwarf at some point, probably turn into a planetary nebula as well, because it will have this giant gas envelope that will be sailing away from it. So, as I said in the last slide, Delta Cepheus does go from 5,600 to just about 6,900, 6,800 or 7,000 Kelvin, depending on where you look. So these are the details of what it's doing. So it's complicated, but what you see is simple. So let's see here. So why are Cepheids important? Why are they still important? Well, back in the turn of the 19th to 20th century, they were looking for a way to measure the Milky Way and to measure the universe. And they really didn't have very much to do that. They were looking at conventional stars and trying to put together a standard candle just based on various lines and spectra. And then they were able to do some parallax measurements, and they were going to use these stars as standard stars to try to lengthen out the baseline that they could use them for. So they had been looking at the idea of using standard candles, and they were just trying to find the proper standard candle to do that. They've been used in the Hubble constant investigation and validation. Again, I don't have details on that. I've not looked into the Hubble constant and how they've been trying to validate it, update it, refine it, but they're still useful for that. And they are a laboratory to test the stellar physics. In fact, all stars that are over 3 solar masses will turn into Cepheids. In order to go supernova, you have to start out your stellar life over 8 solar masses. So Cepheids are generally going to go supernova, at least not very soon, because Cephid, if you remember from the HR diagram that we looked at, these red supergiants include stars like Betelgeuse. So if you evolved into Betelgeuse, I guess you have a chance to go supernova. But I think that with the ability of stars to lose mass through various solar wind kind of functions, it could still get under the either 3 or 1.4 for the what is it, the white dwarf mass limit. For them to go supernova, they have to be over 1.4. So they have a lot of time. They've been around a long time, and they might be able to do it. So they investigate equations of state because they're trying to understand the way the helium works and what's actually driving the pulsations. Again, feeds into investigations of reaction rates and convection, how the star actually transfers the inner heat up into the surface. And one of the things that was on this list was mass loss. So they're actually investigating that as well. Okay. So the stellar system, the system of assigning stellar types is primarily an identification of the temperature of the star. So that's the first thing that you know when you look at a star's designation, whether it's an F or a G. There's a certain temperature range, and then the next thing you see is a refinement of that, like a 0 through 9 number, which refines the temperature area, and then you have some letters that follow it. If you remember on previous slides, the Delta Cepheus was listed as a, I passed it up, where is it? Here, F5, 1b, or IB rather. This IB indicates that it's a less luminous supergiant. So supergiants, it's sort of arbitrary. I guess there's probably some definitions for it. There are some standard stars that feed into this that you make comparisons to. So this is less luminous than your most luminous supergiants. And then there can be other letters even after the IB to indicate other peculiarities related to metals and planetary nebulas, emissions, things like emission lines, things like that. Okay, so let's see here. So keep that in mind. Changing temperature is what drives it from being defined as an F and G type of a star. Things to watch that are used in the MK standard include these list of lines that I'm illustrating here, and to help you identify them, because we're going to watch them change, I've included a number of identification elements in here, principally hydrogen and some other Fraunhofer lines, and I've given you some index marks through this to help you see that. So let's take a look. What does this look like spectroscopically when you take enough spectra in order to fill out the entire 5.4 day? And what you see, you're not necessarily looking for this change in the continuum level. What you really want to be looking at is the change in the size, the width, and the depth of these particular lines. And those are the things, the equivalent widths, the width and the depth, are really what drive the characteristics of each of the star types. So what you're seeing here is the spectra of Delta Cepheus as it goes through its 5.4 day cycle. You'll notice that the hydrogen alpha line really doesn't change a lot or at all in terms of its vertical depth or its width. And the O2 band, this is Earth's atmosphere, a telluric, and this is another telluric. You would expect that not to do anything. It will change with the continuum level, and so that's what you see. You can see the sodium line, the D line, actually changing quite a bit. It gets bigger and smaller. Hydrogen beta is changing, so you get an idea that this thing really is changing its spectra, its spectral type rather, and its temperature as it's being driven that way. So yeah, think about that for a moment. All of this stuff is happening on a star that's hotter than the sun, brighter than the sun, and much more massive than the sun, as well as being physically 44.5 times. So is that impressive? Is that impressive? Does anybody think that's cool? I do. I think that's just amazing. Fast and furious right there. Anyway, so who are the people that we have to thank for this? Who was it?
Back up for a second.
You bet. I like that slide.
What part of this up and down cycle are we in these different spectra?
You would have to ask me the phasing question. And you have caught me totally unprepared. I can't even say that the first one, was at the F phase, and we're going across down into G, because it's hard to tell where the starting point is.
That's all right.
I mean, that might be it right there. I've got the discrete spectra, and each of the spectra.
You owe me an answer, but that doesn't have to be right now.
Oh, I'll write you an IOU for that. That information is embedded in the spectra file itself. There's a Julian date in there. Yeah, I don't. I didn't foresee that question, so my humble apologies. Anyway, so that's cool. The first guy that noticed this was John Goodrich, and as you can see here, he was born in September of 1764. He either was born a deaf mute or through childhood illness became deaf mute. I'm not really sure. His neighbor was a teacher and an astronomer. And after he went through school, and most of the time deaf mutes didn't really go through school, his family was rich. So he was lucky enough to be born into a very rich family, and they were able to send him to a proper school. A deaf mute. Remarkable that he could actually do this. At least he could see, and so that's kind of what allowed him to do it. So they started observing together and working together on other projects. But in November of 1782, he found Algol varied over a period of 2.9 days, and later suggested that it was a binary. And for that work, I mean, he wrote it up and he submitted it to the Royal Society, and he was given something called the Coakley Medal for his work on Algol, and that was all very good. So the following year, he identified Delta Cepheus also as a variable, and a lot of people tried a lot of binary orbits in order to use the tool that they understood. I mean, they knew that binary stars would have eclipsing periods, they would change brightness, and nobody could ever work out an orbit that was satisfactory. I don't know if they tried 3 or 4 kind of star configurations. Those would be very complicated. I don't know that they would be able to do that in this time frame. But he is credited with the discovery of Delta Cepheus as a variable. And ironically, he died of pneumonia in 1786. And the pneumonia was attributed to his nighttime habit of being out looking at the stars without proper clothing and such. So he didn't live a very long life, but he was able to contribute to astronomy during that period of time.
He accomplished quite a bit for 5 years.
Yes, yes. How many of us have done that? None. Yeah. We have to wait about 120 some years for the next person to pick up Delta Cepheus and run with it. And that person is Henrietta Swan Leavitt. And her parents were George Leavitt and Henrietta Swan. And she was born in 1868 and died in December of 1921. She was 53. Our first observer, finder of Delta Cepheus, died of pneumonia. She died of stomach cancer, and that's bad enough. She attended Oberlin College, which I believe is in Ohio.
Oh yeah, something like Cleveland.
Yeah, you say that disparagingly. It's Cleveland. She went there as sort of a college prep, but she did graduate from Radcliffe. In 1892, she graduated with a Bachelor of Arts. Her major was art, as a matter of fact, but she minored in mathematics and astronomy. Astronomy was apparently developed as an interest while she was at Radcliffe, and she volunteered at Harvard Observatory in 1895. And she was working on something called the Great Project. And the Great Project really had scope that you really have to like, because they had been taking pictures of stars through the great telescopes for a while at this point. So Harvard itself had a lot of plates. And the goal of the Great Project was to identify the magnitude of every star on every plate. That's awesome. So you talk about plate solving. You have to be able to do plate solving, and you have to be able to identify the location of every star on that plate so that you can assign a number to it and someone else can go and find it. So this woman had looked at thousands of plates and thousands of stars, and so was very familiar with the night sky. Her ability to do this is key to her later contributions of finding Delta Cepheus and its secrets. So it's interesting the way this builds. She eventually, her hard work was rewarded by becoming the head of the photometric department, and she was defining standards for actually identifying the brightness of stars in a standard fashion. She has work published in 1912 and 1917. And her methodology was extended to 21st magnitude stars. So that's pretty good. And her work on galactic stars involved discovering 4 novas and 2,400 variable stars of her own in the Milky Way. Now, at that time, her 2,400 accounted for a little over half of all the known variables. That's dedication. That's, again, amazing. So while at the Harvard Observatory, she cataloged over almost 1,800 variable stars in the Magellanic Clouds. And 25 of them were found to be Cephei types. And here's her major contribution to astronomy. When she arranged the stars in increasing periods, she found that the brightnesses were also categorized in proper order as well. And so obviously, if you go the other way, you know, the brightness and the periods will then be properly cataloged as well. And so this image on the side is a graph of that relationship she found. So she showed that brighter Cepheids had longer periods, which is what you come to here, and that it's a fairly simple relationship if you can draw a straight line. So that standard candle that I had mentioned that they were looking for, doing all these spectroscopic studies, was found. This was the standard candle that they needed to determine cosmic distances. So why didn't they use the Cepheids and the large Magellanic Clouds to say that, aha, you know, these galactic nebulas really are not galactic nebulas, they truly are standalone galaxies? Well, you're really only talking about a fairly small difference at the time. You know, the Milky Way galaxy is what, 150,000, 106,000 light years across, and the distance to the Magellanic Clouds is about 150. So you're kind of within the air. You could really argue about how much of that difference would be accounted for in error and just, you know, novelty of the technique. So it wouldn't be definitive. You needed something really a lot more distant in order to make that happen. Enter Harlow Shapley. Harlow was an American-born astronomer. He died in 1972, and I have to admit, I don't remember seeing notices of his death in the paper. And we were reading the Tribune, Chicago Tribune at the time. He was head of the Harvard College Observatory, and so worked with Henrietta. And he took her work and turned it into a tool that could be used. He did extensive work on it and had extensive publications, as you can see, in 16, 17, and 18, and 1920. I couldn't find the photographic parallaxes that would really be the ultimate. A lot of these papers you can find online, and I didn't find this one. It would be interesting to find it and read it. So he took her work and created the mechanical system in order to calculate the distances. And so what I just said about the Magellanic Clouds, it just wasn't quite enough for him to make the claim that Hubble did. But it was there. And so he did a lot of the hard work to get that done. In 1920, he also participated in something called the Great Debate with someone that we have no idea who he is anymore, Herbert Curtis. Curtis took the right side. He said that spiral nebula were really island universes, but Shapley said that spiral nebula are all inside the Milky Way. You have to remember, at this time, you know, the 60-inch telescope was really pretty big, one of the biggest, and the Hooker 100-inch telescope was still kind of, it took forever to build telescopes back then. So all the telescopes they had were, rather by today's standards, small. And most of the galaxies that we look at through our telescopes, they look more like nebulas, more like smudges. You have a hard time seeing visually, you know, any stars in a galaxy. Although with today's cameras, it's a lot easier to resolve that sort of thing. So the technology just wasn't there to get it done. In fact, he went so far as to oppose Edwin Hubble in his opinion that they were island universes. So my take on this is that he's actually a data-driven scientist. You show him the data, and he'll go with that data. And that's exactly what he did when Hubble presented him with the data to show that the universe was really a lot bigger than just the Milky Way. So Shapley, the summary of this is that he validated the tools Hubble needed in order to make his, his groundbreaking breakthrough. So Mike did a terrific job of giving the background, the history on Hubble. So, and there are a lot of books on Edwin Hubble. So I didn't include any biographical information on him. But this is just a visual on what he did. He found a variable, a Cepheid variable in Andromeda Galaxy and in M32 and in M33, and was able to work out the distance using the period luminosity relationship in order to identify the fact that that Andromeda was 2.1 million light years away, which greatly exceeds the 106,000 light years. There's just no question. In fact, it was only later learned that there were two populations of Cepheids. And so the Cepheids that he discovered, he was using like the wrong constant, and his estimate, his calculation showed that it was only about 1 million light years away. Still, even with a 50% error, he was able to convincingly, and they didn't even know it at the time. It took other research in order for them to find out that there were two populations. And I believe Shapley did some of that research. It still proved that the Andromeda galaxy was well outside of the Milky Way. And as we know, the rest is history. And the anniversary of that is coming up. It's somewhat difficult to actually fix the point in time, whether it was 1923, 1924, or 1925. There's papers that kind of indicate all three dates. He had been doing the research, writing up papers, talking to other people. But in January 1st of 25, the paper that he wrote in order to roll this out to the public was read at the AAS conference in Washington, D.C., January 1st of 1925. So that's the late date. So we can call it 100 years, only 100 years now that we know that. I mean, my mother-in-law was born within that time frame, right? And so it's possible you still know some people that didn't have the privilege of knowing that the universe was bigger than the Milky Way. So anyhow, yes, Hubble's findings fundamentally reshaped our world by showing the spiral nebula were in fact island universes. But what does this look like? What does this look like when you put it down on paper? What tools did Shapley bring to the table here that allowed him Hubble in order to calculate these distances? And this is basically what it is. This isn't exactly some exotic string theory, advanced calculus laden method that requires you to make all these assumptions and do exotic things. This is pencil and paper work with a difference. So the first example, and by the way, this comes out of Burnham's handbook from 68, 70, whatever it was. And so it's a lot after the fact. So I think this is still accurate. What you do is you take the period of this is the distance calculation, by the way, to I don't know how to get rid of this thing at the top. This is the calculation to determine the distance to Delta Cepheus itself. And we know that Delta Cepheus has a 5.4 day period. And this photographic range of 4.1 to 5.2 has to do with how they defined the brightness on the plates. So it's different than what we have today. I'm not sure what the conversion factors are in order to get it from what we have today to what they did back then. But it's called the photographic range. And these are kind of the givens of the problem, but these are the things that you have to discover with your telescope and taking your images and doing your light curves in order to figure this out. So using the population 1, and I mentioned there are two populations. This is a known population 1. The others are the population 2 have to do with globular clusters, Cepheids that are in globular clusters. They evolve differently for reasons that are totally unknown to me. So you take your 5.4 days and you put it onto the period axis on the graph, and you go up the curve, and you hit the curve, and you go over to the photographic absolute magnitude line, and you find out that the absolute magnitude of this particular star is magnitude minus 2.9. And then you go out with your telescope and you measure its normal magnitude that we see in the evening, and that gives you the two pieces that you need, the apparent and the absolute magnitudes, to calculate your distance modulus, right? So again, a little bit of astronomy here to get the apparent magnitude. And then you find your distance modulus. It's 7.55 magnitude, simple arithmetic there. And then you go to your table. You go to your table down here for the ratio of brightnesses for a known difference in magnitudes, and that tells you that it's a ratio of 1,000. And then you plug it into this simple equation that says 32.6 light years. This is your parsec to light year conversion times the square root of 1,000. It gives you 1,031 light years. Now, Wikipedia says it's actually 886 plus or minus 26, but there's some rounding in here, and I think that's pretty close. So notice this is really simple stuff. This doesn't get your name on a telescope, on a space telescope. This is stuff that Shapley did, and his name's not on a telescope. The trick is in here. The trick is in finding the Cepheid, determining its period, and then identifying the absolute magnitude of that, measuring its apparent magnitude's not that hard. You can do that from Earth, but you have to be able to resolve the star. So as a second example, we're going to calculate the distance to the Andromeda Nebula. So this is what Hubble did. This top line is what Hubble did that earned him a telescope. The rest of it, Shapley and Lovett did, and their names aren't on any hardware at all that I know of. Maybe a building at Harvard, maybe not. So he took the pictures, he took the images that we looked at a few slides back, and determined that this particular Cepheid, V1, had a period of 42 days and a photographic range of 18.8 to 19.8. And you plug it in to the same chart, and you get your absolute magnitude, and you come back to you go back to your table 3, and you have to know one more trick, and that's because if this is logarithmic, you can take your numbers apart. Your 24.1 isn't something that's on the chart here, so you simply take 16.5 and subtract it from 24, and you find the nearest number that's on here and subtract that from the remainder, and then you find that you're left with this remainder of 0.1, and oh, happy day, that's on your chart. And then you just multiply all of these ratios together, and you get this fairly large number, which at the time Burnham's was written was not a very easy number to take the square root of, not accurately anyway. But now it's not even a hard calculator operation, and you come up with 21.2 million light years. So you're a bit low, but still not too bad. And this is just one. He had what did we say, 24 or something Cepheids to average his distance calculation on. So this is what Hubble got his telescope for, the work that went into identifying these particular parameters. So there you go. That's Delta Cepheus. That's why I think Delta Cepheus is quite an amazing star. You can go out and you can look at it. You can follow in their footsteps. You can be amazed at all of the things that it does and all of the way it changes its size. its temperature, and so on. So I highly recommend you go out and do it. It's not a hard exercise. The most difficult part is finding it. Use binoculars, naked eye, what have you, and I think you'll be surprised at how interesting it turns out to be. So that's it. How have I done on time? Yeah. Any questions that I can answer? You can ask all the questions you want, but I'm going to beg off if I don't know anything about it. Okay. Thank you for your kind attention. Appreciate it, and I hope you enjoyed it.
You guys are
Any questions, Larry?
interested, I can do a little.
Thanks, Joe.
Yes, let me segue to that for you.
Thank you.
Kent. Let me get out of the way. Shut this down. Usually at the end of the presentation, if with or without, we usually do something called a show and tell segment, where we show either astro photos that we've taken or just another topic of interest. I've made spectral presentations. And so let me turn it over to Kent. And I have a few astro images to show if anybody's
just on my bucket list. Originally was going to go down to Texas coast, and then Corpus Christi can be pretty cloudy. So then I was thinking about southeastern New Mexico. Then my wife didn't want me driving all the way out there by myself, so I had to make the trip entertaining. And so we went to Albuquerque, and we got to see some balloons. Had a really nice viewing site on the east side of Albuquerque at the Sandia Foothills open space. There's like neighborhood right up to this, and then the neighborhood is just in, and it's open space. And it's a trailhead here at the end of Copper Avenue. And this red line is the dead center line for the eclipse. So I was within a mile of dead center for the eclipse. So that was pretty awesome. And you'll see why, because I got a perfect circle of sun on this eclipse. So I was well equipped. I took my solar projector along, had my 72 millimeter refractor with a solar filter and my Canon camera on it. And then just for people to come and look through, it took my 4.5 inch reflector with a solar filter. And we had it was actually kind of cool to look at with solar glasses too. So I'll show you my refractor. There you go. Okay, now hopefully you can actually see something. So then with the refractor, I had my Canon EOS RP on there. Used ISO 250, 100th second exposures. I played around a bunch with white balance because a glass solar filter will look very yellow orange, but sunspots always look a little fuzzy to me. And I played around with white balance. I found that a white balance at 2600 made the sun look just sort of gray here, but it gave crisper sunspot focus. Unfortunately, I kind of hurried and messed up my focus. So my sunspots actually, my practice ones looked really good. The actual eclipse here, I didn't have it perfect focus, but anyway, that's the way it goes. And then this was eyepiece projection, so that the sun was actually taking up most of the image. So if you're familiar with C1 is like when the moon first touches the sun. C2 is when it's like all the way inside, so that starts the annularity. C3 is when the annularity ends, and C4 is when the eclipse ends. So this is 4 minutes in. Got a couple nice sunspots up there in the top, which kind of help you keep track. 32 minutes in. 48 minutes in. Getting close to eating the sunspots there as the moon creeps on in. Hour and 1 minute. So annularity was about an hour and 20 minutes from the start. So we're getting closer. We still got about 20 minutes to go to get annularity. There's an hour and 12 minutes. Hour and 21 minutes. Okay, this is basically C2 right here. Oops, I'm drawing on the screen there. Actually, I'm not even in projection mode, I don't think. There we go. Oops, sorry. Now I got to hurry through all those slides again. Okay, that's where we were. Nope, one more. And then 25 seconds later, it looked like this. So we went from not quite closed to definitely a circle, but it's obviously still a bit of an oval there, thicker on the top. This, according to my time, is about 15 seconds before maximum eclipse, but it's my closest to circle. Actually, looking at the camera, I thought the next image was the perfect circle, but I've realized making this slide presentation that in another 20 seconds or so here, what's the difference here? Let me look at that. From 3654 to 3719, it's actually a little bit thicker down at the bottom here than at the top. Not much. It's still almost a perfect circle. So there was 4 minutes and 50 seconds worth of annularity. Actually 4:55, I think.
Was it noticeably darker then?
If it would have if it had gone from no eclipse to that in a minute, you would have greatly noticed it. Because it's so gradual, you didn't really notice it. You could tell, like, it's darker now, but it happens slowly. Now, the one thing that I knew to expect, it was about a 40-degree morning in Albuquerque that morning. And by the time the eclipse was going and the sun's out, it was clear. There were a few stray clouds around, but they never interfered at all. We had a perfect day. As it warmed up, I took a jacket off. I was, really nice and comfortable out there. And as it got to about 85%, all of a sudden it's like, man, I could put that jacket back on. It got noticeably cooler. And I knew from 2017 that there would be that effect, except it was hot summertime in 2017. So it just went from a blazing hot Kentucky afternoon to like a fall day. It was actually starting to get chilly again on this one. It was the temperature difference was really noticeable. And some of the hikers that were out were talking about it.
Could you see any stars?
No, there's still 10% of the. I didn't see it. What was it close to the sun at that time?
It should be close enough.
Okay.
I mean, if you had a good blue sky.
Yeah, I didn't notice. I had a good blue sky, but I didn't notice Venus. But my telescope was.
I don't remember. You had to block the sun out.
Yeah.
Yeah.
We saw Venus and a handful of bright stars in Kentucky in 17.
Yeah, I saw some stars in Kentucky. I got image with some stars. And so then the moon just keeps going away. So this is about 15 minutes past annularity there. 30 minutes. 50 minutes. Starting to get a sunspot back there. They've been hidden for a while. Hour. Got both sunspots back. And this is hour and 25 minutes after annularity was over. And it's 4 minutes and 10 seconds from the end of the eclipse. My next photo was full sun because I was doing 5-minute images. So my next image was back to full sun. So I showed you about half of that. I actually have about 40 images of the whole thing. Kind of summarized here. You start here and goes down and then goes down each column. And then the one I just showed you at the end is the red arrow over there. Ended up, I think, with a pretty nice, certainly way better photography than I managed in 2017. So about 1,000% better than what I was doing in 2017. The real crowd pleaser is my solar projector. This thing worked beautifully this day. It's a little susceptible to shaking in the wind, but it was dead calm. That's why the balloon festival is in Albuquerque. It tends to be very calm there that time of year. So that worked perfectly.
What kind of refractor is the solar projector scope?
It's an old Tasco that I had as a kid. I think it's like about 2-inch.
Yeah, 60.
Yeah, yeah. And then I've got a lens that I took out of, it doesn't have an eyepiece on it. It has a Barlow lens out of a 35mm camera in the place of an eyepiece. And that's what gives you that 3 to 3.5 inch diameter solar image on there. That's actually in focus. I think I had better focus with some of these cell phone pictures of this. My wife took these pictures. For the next eclipse, I'm actually going to mount the camera right on the solar projector because she kept taking them from different angles and stuff. So and make it a little more consistent, but got kind of the same series of images here. 1037 is the dead center again. And solar projector was really nice for that too. And then we've got one where it's kind of starting to break up on the edge up there as we get close to C3. And then of course it goes away again. 12 noon is like 9 minutes from the end there. That last one's. I just wanted to compare two of these that I took. One with this one I just talked about how it's kind of fading out there, and you can see the exact same pattern of fading in the picture I took with the camera with the refractor telescope. So that was the eclipse. And this trip had some bonuses like visiting friends in Iowa and Colorado, but it also had the bonus of going to Great Sand Dunes National Park. If you don't believe these are great sand dunes, can you see specks right in through here? Well, little tiny specks, those are people. Let me do it for the computer. Okay, so the specks are right here. There's actually some people on the ridge. Oh, right there. Those are people on the ridge right there. I think one of these dunes is over 700 feet tall. They dwarf any sand dunes I've ever seen anywhere. And I've seen quite a few sand dunes. Very pretty place. This is looking southwest at sunset. And of course, this is where the best part of the Milky Way is going to be. That part of the sky was cloudy all night. Yeah, I was a little annoyed by that. But I did get some reasonable shots. I don't know how well you can see that. I might have to kill all the lights. I don't know. Do you guys see something there? Yeah, it's a little. This one's good because I have 4 or 5 images. I think I can do some image merging. This is just a JPEG. I haven't done any kind of processing on this. So I think I can do some work with these. But just to orient you a little bit, that bright spot in the middle of that circle I just put over there, that's Andromeda. And then going straight overhead up by the summer triangle, I think I got a better image. So it was kind of fun to do some dark sky photography. I learned a lot, made some silly mistakes. I actually tried to do a 30-minute star trail. And somehow I bumped my F reading on a camera when I set it up. And so instead of F4, I did it at F22. So I saw nothing. It was like, and I wasted 30 minutes on it, no less. You know, oh well. Live and learn. It's also a pretty place early in the morning. And so, of course, next thing up will be April 8th this coming year. This is actually a shot of mine from 2017. And that's all I got.
Beautiful.